Okay, so you now run the GM and you did the G previously. So the question is a bit, if you can already do G-blob and you're interested in breeding values, how does it help to add the M component, to add the methylation component in this GM-blob model? So just doing it like this and not trying to do any more sophisticated modeling, the M component or the autonomic component may help to explain an existing variance structure in your data that your G-blob model may not capture. So if you don't capture that structure, then maybe the assumption of your model that the residuals are IID, so that they're independently and identically distributed, may not hold. So it can, in principle, it may help to actually make a better model. As I said, it may actually help to predict phenotypes, if you're interested in that, rather than predicting breeding values. And that can be many different ways. You can just have it in the GM-blob as a separate component. It could be a correlated trait and a multi-trait G-blob kind of model, or in a hierarchical kind of model, like the GO-blob. So these are, let's say, positive sides of it. The negative side is that if you're interested in breeding values, the M component or the autonomics may actually absorb genetic variance. And that's maybe not what you want, because if you then only use the breeding values of your model, the autonomic component may have removed information from that, useful information. So there's also sort of things that may be going on. There may be an interaction between G and M, between the genotypes and the methylation scores that you could potentially consider in your model. There may be a covariance between those models. So what we will do then is take a model that has been presented as scored GEroNIMO. I'll turn this here for blob, just to be consistent with the names of the other models. If the other omics are partially heritable, then we can use this GO-blob model that was developed by Gibson and Lagara. And if you want to keep all genetic variants and the breeding values, we can use a model that, with methylation, we term it GMC-blob. And this is something that we've developed here. But I'll talk you through each of those different ones. So if we want to capture the interaction between the genotypes and the methylation, the easiest thing, well, we can just add in a random effect for that interaction. And this random effect has a relationship matrix. I call this here J, that can be computed by taking our G matrix and the M matrix and just do an element-wise or so-called Hadamard product between the two matrices. So what does that mean? It means that any element Ij and matrix J is simply the product of the corresponding elements of G and M. It's really that simple. So even in R code, although you multiply two matrices, you actually just do as if it's a regular multiplication, and this gives exactly what you need. What I said before is that for the M matrix, we want the diagonal element of that to be 1. So we can interpret the variance that we estimate for the M component. And the same holds here for the matrix J. So it's we want to, let's say, tune it such that the diagonals on average have a value of 1. But if we look at the expectation of, if we compute it like this, of these diagonal values, then that's the expectation of these, the product element, was product of the diagonal values of J and M. And these are, if these are independent, we can write them as a product of their expectations, and each of them have an expectation of 1, so this expectation should be 1, which means we can just do the computation like this, and we don't need to standardize this matrix any further. Right? And then if we add this as a third matrix in the model, that will also get a variance, and that variance tells us how much of the phenotypic variance is due to the interaction between genotypes and methylation. So that's interaction, and now we're going to look at covariance. So interaction and covariance are not the same. Sometimes if people think about this, okay, these effects may not be independent, let's fit an interaction, but it's good to realize what the difference between those two things is, right? So an interaction would mean, for instance, that the effect of the genotype depends on the level of methylation in a way. Whereas a covariance means that the effects of the two are not independent from each other. And that's not the same thing. So, well, here what we may want to do is that we want to model the covariance between the random effects. And the approach that's taken here is that the covariance between the two components is modeled as a separate random effect. And that's, well, perhaps a little bit confusing at first. But what we need to do is we add a third variance component or random effect to the model, and that's actually going to explain this covariance. So we need a third matrix in addition to our matrix J and K. And that matrix, the way it's computed, can be interpreted as if it's, let's say, the square root of the matrix J times the square root of the matrix K. Right? So that would be if you have just the variance of one, let's say, of one variable and the one of another, and you multiply the two with each other, the variance of that multiplication, then they look like something like this. So, but how do we compute the square root of a matrix? And for that we use the Gillespie decomposition. So we take the Gillespie decomposition of the G, and we take the transpose of the decomposition, we multiply it with the Gillespie decomposition of K. And that gives us a new matrix of term S near C that we add as a third variance component in the model. So this has been invented and published some 5-6 years ago. And I thought this was actually quite a neat way of doing things. So that's also one of the models that you will be running this afternoon. So the GoBlood model tries to model, let's say, how the effect of the genotypes of the genome is mediated by the other omics, in this case, the methylation. And it's actually, to run this, you need to run two subsequent models, as I'll show in a minute. So in that sense, we can say that Goldblatt is a hierarchical model, right? There's two papers that have presented this. There was originally a paper in 2021 in genetics, and there's a second one in 2023 in JDS communication. So if you're interested in this, I would recommend reading the second paper because it's more accessible than the first one. But if you want to know more details, maybe the first one. So the first one actually has 3 methods described to run this model, and I'll explain 2, and you will also work with those 2 this afternoon. So how does it work? The first method, there's 2 models, as I said, and the first one is in principle is what I showed for the GM blood model, but in this case, the M component is actually modeled as a regression on the methylation scores. So remember this morning we talked about G blood and SNP blood that are fully equivalent. So if we have M blood, we can also do a fully equivalent of that, where we don't have this matrix K, which are the methylation relationship matrices, but there's a random regression on the CpGs or the methylation scores directly, right? So that's what we have here. This component is actually comparable to G blood, and the second one here is comparable to M blood, but it's just parameterized differently. But it's parameterized differently such that we get an estimated effect for each CpG site on the phenotype. That's the aim. So that's the first model. And then the second model, actually, in the first method, estimates breeding value, so we can use G blood for that, for the methylation scores. So not for the effect of the methylation, but for the methylation scores themselves. And that means that we have one model for every CpG site down. So if we just write this down, then our Y value in this model is a methylation score for CpG site I. And we try to explain as much variance in there with the SNP genotypes. So it's a G block or SNP block kind of model. Doesn't really matter. So the connection between the 2 is that this matrix M, every column in M, holds the methylation score for one CpG site. Right? So there in the first model, we have all of them together in the model. Here we do each CpG site 1+1. Then we get estimates of the different models. We get the U has a subscript R, so it's like, let's say, a residual breeding value next to the methylation effect. That's where the subscript comes from. We get estimated effects for the CpG sites, alpha, and we get estimated methylation scores partitioned to a breeding value, a heritable component, and a non-heritable component, right? And then finally, the residual up here from the first model, that is, let's say, the true residual, which is unexplained phenotypic variance in our phenotype of interest. So now, given those 4 estimates, there's 2 quantities that we want to compute. First, it's, let's say, a total breeding value, and the other one is the non-heritable methylation effect. And I'm stating here that it's non-heritable because the effect due to the methylation that has a heritable basis is included in this total breeding value. So what we do is that to get this total breeding value, we take this breeding value of the first model, and we sum across all the CpG sites the product of the breeding value for the methylation score. So the part of each, the the methylation score of each CpG that's heritable, and we multiply that with the effect of that CpG site. So that's the, let's say, it's an effect that's associated with the methylation, but it has a heritable basis because this is a breeding effect. And then the non-heritable methylation effect is actually from this model, everything that is not heritable, so this residual, but then that's the residual for the methylation score. So to get the effect on the phenotype, we have to also multiply this with the estimate of the alpha. So the first model is just one model. The second model, you run this as many times as you have number of CpGs. So the number of analyses that you have to do can quite a bit. So this is one of the reasons why this morning in the beginning of the script, I said I tried to reduce the dimensions of the CpGs quite a bit. So we're now a little bit under 3,000, but it means that you're going to do this, you're going to run close to 3,000 models. So I think that the thought behind the goblet model is probably best understood from this method 1, but the method 2 is more practical. Method 2 also has 2 models. And the first one in principle is fully equivalent to GM blood. So we have a breeding value like in G blood, and we have a CpG effect or methylation effect like we have in M blood, right? So we can actually use the methylation relationship matrix here for this component C. And then what we do, so from this first model, we get estimated effects per individual due to the methylation. And then we split that effect due to the methylation in the second step into a heritable effect or breeding value and a non-heritable effect. So here we get the estimates from C in the first model. There is an estimate because we put a hat on it here. And that is the Y value of the second model, which can be a G-block kind of model, right? Again, as for the first model, we are interested in 2 quantities, the total breeding value and the non-heritable methylation effect. So the total breeding value in this case is the breeding value of the first model, and then it's the breeding value of the second model, which directly models the heritable part of this estimated methylation, individual methylation, right? And then the non-heritable methylation effect is the residual of the second model. So anything in the methylation effect that's not explained by the SNPs goes into the residual, and is this second component here. So what both models achieve is that everything that's heritable will go in the breeding value, and the effect of the methylation that's not heritable goes into a separate effect in the end. Right. So this is just to indicate where all the different things go to. And as for method 1, the true residual of the goblet model is the residual of the first model of both the method 1 and the method 2.
Yes, here we are assuming that U doesn't have any methylation effect, any methylation component.
Yeah, it doesn't really matter, because the idea here is that anything that's heritable, whether that's mediated by the methylation or not, should just go in the breeding value, right? So if in this first model, this U actually captures some part of the heritable part that's mediated by the methylation, we don't really care, right? Because it would come back to this total breeding value in the second step anyway. Yes.
Just to clarify, so the first method we calculate the breeding value per CpG island.
Yes.
And the second one is a breeding value per animal, basically on the methylation score.
On the methylation effect.
on the methylation.
Yes, right.
Now-
So here we estimate breeding values for methylation effects.
So we don't
Effect
know
on the phenotype.
how, like, both these methods, they will give a breeding value either way. Like, especially the first one, I would like it is to give some TPG island that has zero effect. Like,
Yeah, so I think the first one is a bit more refined. Because in principle here, what you can do, you can consider that each CPG has its own heritability, right?
it's a candidate.
And that can be easily modeled here. Whereas in the second model, there's just one heritability for the overall methylation effect. So it assumes that every CPG site has the same heritability. That's an implicit assumption. So this is more practical and easier to run. I think the other one is perhaps more correct. Okay, let's see. So then we have this GMC blood model that we've developed in actually in the GeneFridge project, described in the paper by Galina Perez. And then within the context of the GEroNIMO project last year, we had Valentin Haas from Germany visiting with us. That was actually the year before, because he was really interested in this model, and then we revisited and we came up with a more formal derivation that's a little bit different, but the principle is still the same. So here what we want to do is we want to make the two components due to SNPs and methylation independent. Sort of before running the model. And that ensures that breeding values are fully explained by the SNPs, which in principle the GoBlob also does in the end, right? Because it looks at what is explained by the methylation, but what of that part is heritable, take it out and put it in the breeding values. And here we want to, let's say, define our model such that anything that's heritable automatically goes into the breeding values. So what we want to do is we want to avoid covariance between the G and the M. And that may also improve convergence of the model as well. So what we did, the approach that we took, we removed variation in M and in the methylation scores that co-varies with variation in G. So the implication is that we really remove any heritable variation in the matrix M from that matrix. Or to put this more formally, we can say we condition the methylation information on G or the SNP genome. So we compute one conditional on the other. How do you do that? So when I derived this first, actually the thought that I followed exactly like this one. So I thought, let's regress the methylation on scores for each CPG site on all the SNPs to remove the heritable part, right? So this is very similar to this second model of the first method of GoBlob. We regress just methylation scores on SNP genotypes. And the residuals of this model are actually methylation scores that are conditioned on the SNP genotypes, or they're not heritable. That's the idea. So if we go back and there's no fixed effect in this model, and we model this as a SNP kind of model, the SNP estimator of G in this case, so can be written as follows. And then what we're actually interested in is the residuals of that first model, because that's where all the heritable part of the methylation is removed, right? So this estimated residual of the first model we can write as, we can rearrange the equation and we can subtract the estimated breeding value for the methylation from the methylation itself. So here we have G hat, but this is the observed methylation score. And then we substitute this GI by this expression here. And then we get this somewhat complicated formula, but we can rearrange this and it comes down to something like this. And this matrix is known in statistics as the smooth matrix. So for one CpG site, we can just compute this entire matrix and multiply it by the column of methylation scores. But if we have this matrix and if these heritabilities of all the methylation scores are the same, which is not necessarily the case, but if we make an assumption, it means that we can directly compute the condition methylation scores as taking that orange equation there and multiply it with the full matrix, right? It's the same as doing this for every column separately. You can directly compute it with this matrix. So, well, once we have this, and then here, what we originally did in the Paris et al. Paper is we assumed that this lambda is then equal to, well, it's proportional to the average heritability of the methylation scores. So when you run this afternoon, that will actually grab these heritabilities that are estimated from the Go-blood model to be used in this one. Now, well, and then we go for lunch, but so when we had Valentin Haas over, we also had somebody from Spain, Theo, I don't recall his last name, at least I can't pronounce it. And he was also interested in running this model, and he was going to do this. He had a data set of something like 300 individuals. And this Z prime Z is a matrix that has dimensions numbers of SNPs by numbers of SNPs. But he had whole genome sequence on his individuals, so he put like 1 million SNPs in, used all the math, and then he had this 1 million by 1 million matrix and tried to invert it in R, and then came back and said, it doesn't work. Which I said, well, that's not a surprise, but anyway. So what we then did is we revisited the math, and rather than using Z prime Z, you can also write this in an expression where you use Z prime. And then we are actually very close to the genomic relation matrix G, right? So, and that's also what's used in the code for this afternoon, but it's explained in the Haas et al. Paper from last year, how to do this computation instead of using this expression, but using it as an expression of G and G inverse, which is fully equivalent. Only if you have that many SNPs, the implementation with G is feasible and is very quick, actually. Okay, good. So that's it. And if we come back after lunch, you can run these next models, and that's still doing variance partitioning. The Go-blob, there's the two implementation. The first one does run the model, the second model, the reading value for the methylation score for each CpG site. So that does run almost 3,000 models. But I reduced the chain length by a factor 10. So it's still, it takes some minutes, but it's doable. So don't be surprised if that takes a bit longer than the others. And Levi noted that there's a typo around line 335. Today was in this expression, there's an underscore missing, and you need to add that, otherwise that will not work. So you may want to fix that before running the code any further. Unless there's any quick questions, we can now first go for lunch, I would say.